Hello students, in this session we are going to look at logic gates and a little bit of Boolean algebra. So all semiconductor devices would work on these logic gates. Okay, these logic gates are building blocks to our semiconductor devices. Now take a look at this. This is what we call as the AND gate. I hope you recognize that. There are three types of gates, major building blocks. So this you see here is the AND gate. To remember, you imagine this as the D, okay? So it looks as the D, so AND gate. This one is the OR gate, and this one is the NOT gate. These two, A and B, are the inputs. So when will the AND gate give you a positive output? So 0 means off, consider 0 means off, and 1 means on. So an AND gate will give you a positive output, or it will give you on only when both are on and on. In other words, only when both conditions satisfy. If this is also 1 and this is also 1, then only the AND gate will allow 1 to be the result. Okay? So in all the other cases, you would see AND gate will give you 0. If one switch is on, if one switch is off and the other is also off, the result is 0. If one is off, the other is on, both are not on, then it would still be 0 output. If one is on, the other is off, then again the output is off. Only if A is also on and B is also on, then only the result will be 1. Okay. So this is the truth table for AND gate. This tells you if you change the inputs to on and off, what would be the output? So these are the outputs. This Y is the output of this AND gate. Now let's take a look at the OR gate now. OR gate, it says if either of the inputs give you 1, then the result would be 1. Either B is 1 or A is 1. Then the results are 1. What if both are 1? Well, then also you'll get 1 as the result, because all this gate needs is only one input to be positive. So that's it. So 1, 1 will also give you 1, and that's what you get here. Only if both switches are off, you'll get no output at the other end. Let's take a look at the NOT gate. NOT gate simply reverses the input. By the way, there's only going to be one input in the NOT gate. So if there is A, if A is 1, it will become 0. It just, if A is on, the NOT gate will make it off. If A is off initially, it will switch it on. So that's what a NOT gate does. Then there are other kind of gates, which is a combination of these building blocks, something called the NAND gate, which is denoted by this, something called the NOR gate, which is denoted by this. So these are the inputs, input number 1, input number 2, input number 1, input number 2, different values, yeah? And this is where you'll get the output, 1. So this denotes the NOT gate, and this denotes the NOT gate, and this denotes the OR gate. So NOT and OR becomes NOR gate, and this becomes NOT gate plus AND gate becomes NAND gate, okay? And there is something else called the exclusive OR gate. This is the symbol, exclusive OR gate. So exclusive OR gate only gives you positive value or only gives you positive result when there is an exclusive OR. So if I draw the truth table for XOR gate, this gate, it'll be like this. If this is A, this is B, and this is Y, A, B, Y, exclusively only one has to be positive in order to give you a positive result. That's what it says. So if one is negative and one is positive, you'll get a result as positive. Exclusively one is positive. So that's what. If this is positive and this is negative, again, you'll get a positive result. One, that means a positive result. Switch on, positive result. Then if both are switched off, you won't get a positive result, of course. If both are switched on, that means it is not exclusive OR. Only one input is not exclusively different from the other, okay? So in that case, again, you will get a negative result. That's what this XOR gate is all about. Okay. Sometimes this is used as the fundamental building block of your semiconductor devices, these three. NOT gate, NOR gate, and exclusive OR gate, okay? So this was all about gates, understanding what is the input and what is the output. If you have AND gate, you should be able to write the truth table for AND gate. If I give you the OR gate or exclusive OR gate or NOR gate or NAND gate, you should be able to write the truth table for all this. Okay, once we know the truth table, once we know the inputs and the outputs, let's see how to use that into solving a circuit. See, a circuit might not have only one AND gate. It might have a combination of all these gates that we have discussed. It might have two AND gates and three NOR gates combined in a different manner. And using that setup, we would have to find out what is the output. To do that, we can use something called Boolean algebra. Boolean algebra. Now, there are some identities that you need to remember or understand in order to use Boolean algebra properly. So next, we're going to do that. We are going to talk about this table. This more or less covers all the identities that we have to learn in Boolean algebra. These identities are pretty simple. We are going to discuss the last two identities, okay? Absorption law and De Morgan's law, because these are the most complicated ones. Still, I would just show you one or two. So let's take this one and let's take this one. So identity law. In the AND form, if you have one switch as always on and the other switch can change, okay? So what would AND gate give you? The result. So 1 and 0 will give you 0. 1 and 1 will give you 1. So what do we see? That whatever result we are getting here, it's matching this thing, isn't it? If you look at the truth table of AND gate, 1 and 0 will give you 0. So let's say this is your A, and 1 and 1, if this is your A, is 1. If you just look at this part, A value here, isn't it matching the A value of the result? So that's why we say this must be equal to this. Similarly, if you take a look at all these, you would understand this part is easy. Okay, you can understand that. Let's take an example of this one, okay? A or A gives you what? Let's take 0 or 0. Gives me what? 0. Let's take 1. If you've taken A value as 1, this A is also 1. 1 or 1 gives us what? 1 again. What do we see? That whatever value of A we had taken, the same value we are getting here. That's why A plus A gives us A. It's called the idempotent law. Similarly, we have inverse law, commutative law, associative, distributive law. You can verify these laws on your own. It's very easy to understand. Let's look at absorption law now. This is a little bit complicated, so we'll understand this in detail. The AND form of the absorption law says this. Let's look at how logically this makes sense. A into A plus B gives us what? So we'll apply the distributive law. A into A plus B, this law. This will give us AA plus AB. Now, A into A or A and A gives me A. How do I know that? A and A gives me A. See? A and A gives me A. A plus AB. Now, what I can do is I can take A common. If I take A common, I'll get 1 plus B. What does this mean? 1 or B value. Now, B can be either 0 or 1, does not matter. This thing will always give you 1. Think about it. On or on will give you on. On or off will again give you on. 1 or 0 will give you 1. 1 or 1 will also give you 1. So I know that this thing will always give me 1. So I can directly write this as A into 1 or A and 1, which will simply give me A. And that's how I get A into A plus B as A. I hope this part is clear. Let's move on to the OR form of the absorption law. The OR form of the absorption law says A plus AB is equal to A. Let's find out how. It's very simple now. A you take common, you get 1 plus B. This part you already know, it is always 1. So A into 1 or A and 1 will always give you A, and that's how we get this law. Clear? Yeah. So we used all these other properties to derive or to figure out the absorption law. Now, De Morgan's law is something that you should remember. I'll just walk you through this law. We are not going to derive it. De Morgan's law, there are two forms, the AND form and the OR form. The AND form of De Morgan's law says this. A and B, not of A and B, is equal to not A plus not B. And that is what De Morgan's law says. You can draw the truth table for this, and you can draw the truth table for this and verify. You will see that these two truth tables, they match. Okay. Let's look at this. This form or the OR form of De Morgan's law says that not of A or B is equal to not A and not B. This is the OR form of De Morgan's law. Again, you can verify this by drawing its truth table and drawing the truth table of right-hand side, and they would match. Okay? Now, whatever we've learned here, let's try to apply this into a problem which again came in the NEET exam last year. Let's do that. Okay, so here's the question. It says, a logic circuit provides the output Y as per the following truth table. So whatever is that circuit, we do not know. All we know is the truth table. What is the input? What are the inputs? And what is the output? So the expression for the output would be which of these four options? That's what we have to identify. We know A, we know B, and Y is what we have to find out. Okay. So the proper method would be to just go one by one. Let's pick one option, draw its truth table, see is it matching this? If yes, that would be the correct option. Then similarly, go to this option, see is the truth table matching or not, and then identify the correct option. The other option would be to be a little smart. Just identify, look at the truth table, and we start with this. Okay, let's start with option number 4. It says that the output is same as B. That's what option number 4 is saying, right? That your output Y is equal to B. Is that so? Is the output Y same as B? You will see no. Actually, it's just the opposite. Whenever B is 0, the output is 1. Whenever B is 1, the output is 0, and so on. So now we know this would be the answer. Okay, simply we know what is the answer. But if you want to verify, if you want to go in the proper way, let's pick one of these options. Let's pick option number 1 and try to see whether that matches with the truth table given to us or not. Let's draw the truth table for this, okay? We're assuming this to be y. So for now, we'll forget about this y and we'll try to find out y of our own, which is based on this expression. So what does it say? This expression says a dot b plus a naught. That means when a is 0 and b is 0, a dot b will also be 0. A dot b plus a dash. See, if this is 0, this is 0, and a naught or naught of a, that would be 1. This thing will give us what? This thing will give us 1. Okay. When a is 0, b is 1. A is 0, b is 1. This is 1. Not a is 1. So 1 or 1 will again give you 1. 1 or 1 will give you 1 once more. So what you're getting here, 1, 1. Now here only we can see it's not matching the y that was given to us earlier. The first one matched fine, but the second one, you see, it's not matching. So this cannot be the answer. Okay, if you want, you can try the other two also. If a is 1 and b is 0. If a is 1, b is 0, not a will be 0. So 0 plus 0 or 0 will give you 0. Then if a is 1, b is 1, you have 1, 1 here, and this would be 0. This will give you 1. So 1, 1, 0, 1 is what you are getting if you use this expression. But that is not what was given to us, right? To us, the output was already given as 1, 0, 1, 0. 1, 0, 1, 0. So it's not matching what we got using this expression. This cannot be the answer. Similarly, if you do this, you'll find this is also not giving you the output as mentioned to us. Option 3 is the correct one.